welcome from our side for this RE4Industry knowledge transfer webinar on sustainable syngas production for the German and European glass industry. Let me briefly introduce myself. My name is Rainer Janssen. I'm Managing Director Projects of WIP Renewable Energies based in Munich. We are a partner of the RE4Industry project. I'm also currently president of EUREC, which is the European Association for Renewable Energy Research Institutes based in Brussels, where we promote basically research innovation in the field of renewables. Okay, in this webinar, which we have actually prepared together with Christiane Nelles from BV Glas and Hendrik Steinort from Enviva, we have set up or started preparing this webinar since a few months, even now, to address what is currently a very hot topic, namely how can we replace and substitute natural gas in energy-intensive industries, including the glass industry. Here, I believe we need to look at two timescales. It is short-term. We need to do our best to save and replace natural gas due to the Russian war in Ukraine, which leads to the current shortage of gas and the price spikes that we all know. But there is a second issue, which of course is decarbonization, defossilization of our societies and our industries, which is more mid and long term, for which we also are looking at solutions to replace fossil and natural gas. Now, these are two timescales. There is a urgency. We need to secure the competitiveness of our energy-intensive industries, but still we need to keep in mind that short and long-term measures should be in line, should go hand in hand to move us towards a more sustainable future. Last week, actually, there was a RE4Industry knowledge transfer webinar in Graz, where also these issues were discussed with a number of representatives of energy-intensive industries from Austria. Information on this webinar should be available at the RE4Industry website very soon. And the hotness of the topic was also underlined by the fact that I was invited to give a little interview with the National Austrian Broadcast, ORF, one, where they did ask me, when is the syngas expected on the market? I was careful with my answer. So with this little introduction, we do have a rather large group of participants, which is wonderful. Still, I believe, as we aim to be a working meeting, we would invite all participants to just briefly introduce themselves with maybe name, affiliation, and one or two additional lines. I would do the following. I would invite the participants according to my list there, which you cannot see. So I would I would ask you, and then maybe you switch on your camera, say a few lines, and then we proceed. So first on my list is Alessandro, please.
Good morning. This is Alessandro Carmona from Research Center in Spain. We are the coordinators of the RE4Industry project. I'm glad to be here today. Thank you.
Thank you very much, Alessandro. Much appreciated. Then we have Christiane Nelles. Christiane, please.
Christiane Nelles. I'm the advisor for energy and climate policy at BV Glas, the German Glass Federation.
Thank you very much. My colleague, Juan Ma. So the list is alphabetic, so you can get prepared, no?
Okay. Hello, everyone. I'm a colleague of Rainer, Ingo, and Rita, and I'm here to support you with this webinar. Yeah.
Thank you very much. Next would be Freddy Détier.
Yes, good afternoon, Freddy Détier. I am the the regulatory compliance coordinator for the glass fiber industry in Europe.
Thank you very much. Welcome. Then there is our colleague Duygu Selik.
Hello everyone, my name is Duygu Çelik. I am a project manager at WIP Renewable Energies and I am here to support the webinar today.
Thank you very much, Duygu. Fabrice Rivet.
Good afternoon, everyone. My name is Fabrice Rivet. I'm Technical Director at FEVE, which is the European Container Glass Association. We work closely with BV Glas and with Christiane in particular, and I'm looking forward to hear what you have to say about Syngas.
Thank you very much. Welcome. I would like to invite Franz Vogel.
Hello, good afternoon to everybody. My name is Franz Vogel. I'm working for the German Fine Ceramic Associations, and I'm responsible there for environment, occupational safety, and energy. Thank you.
Much welcome. We would like to invite Giulia Gallo.
Yeah, hello everyone. I'm Giulia Gallo, and I'm also working at FEVE, the European Container Glass Association, as Fabrice.
Welcome. We have Harry Sayanos.
Hi, everyone. Harry Sayanos, I'm working with business development with industrial solar, providing sustainable process heat for industries with a particular emphasis on concentrated solar heat.
Thank you very much. Hendrik Steinort.
Hi, everyone. My name is Hendrik Steinort. I'm a senior associate in Enviva Inc. We are the world's largest supplier of industrial wood pellets.
Thank you. Welcome, and also one of the organizers of this webinar, as I mentioned. Welcome also to Petra Ingelbrecht.
Yeah, hello, I'm the colleague of Frederic Détier. I'm a sustainability leader for the European composite business.
Welcome, Johan Overath.
Yes, my name is Johan Overath. Hi, everybody. I'm also from BV Glas, and I'm the Director General of BV Glas. Thank you very much.
Welcome. Caroline Seefeld.
Hello, Caroline Seefeld. I am a sustainability advisor for Total Energies. So we're working on renewable fuels.
Welcome. Invite Jörg Leicher.
Good afternoon. My name is Jörg Leicher. I work with GWI, Gas and Wärme Institute in Germany. We are an independent research organization focusing, among other things, on decarbonization of process heating.
Welcome, Manolis Karampinis.
Hello, everyone. My name is Manolis Karampinis. I'm Director of Business Development of Membership of Bioenergy Europe, the European Bioenergy Association.
Welcome, Manolis. Then we have Mark Bailey. Mark, can you hear us? Okay, I would
yes,
like
sorry.
To, yes, okay.
Good afternoon.
Yeah.
Mark Bailly from Unifit, Belgian Association.
Welcome. Then we have Ferdinand Düner.
Hi, yeah, I'm Ferdinand Düner. I'm part of the HVG, which is the, I'd say, complementary association to the BV Glas, more on the technological aspect. And yeah, I deal mostly nowadays with sustainability in glass production.
Welcome. Then we have John McVeigh.
Yep, thanks, John McVeigh. Owens Corning Energy lead here in Europe. So looking after purchasing gas, electricity for our sites, carbon renewables, things like that. Thank you.
Welcome, excellent. And then finally, I would like to invite Myrto Senelli.
Hello, I'm from CERT Research Associate, and I'm working with the rest of the colleagues in RE4Industry, so I'm here to support for the webinar. Thanks.
So excellent. I hope, did I forget someone?
Yes,
maybe me, but I would also introduce myself.
All good. I'm sorry. The organizer. Olga, it's horrible.
No worries. I'm Olga Birge. I work at WIP Renewable Energies with Rainer, and we are happy to see you all here.
But I would have introduced you anytime, Olga, for your presentation. But
Yes.
accept my apologies. Sorry.
Also, Mr. Bleul.
Yes,
Yeah.
Thomas Bleul also. Yes.
Yeah. My name is Thomas Bleul, CEO of Spanner Re2. We are for the last 15 years in Syngas, totally focused on CHPs. And now there's a lot of interest from a lot of industry to start replacing natural gas. And yeah, later you will see a short presentation from ourselves to get you informed where we're at and where we may see a future. Thank you.
Very good. We look forward to yours and all the other presentations. So now we will start the webinar with a brief overview given by my colleague Olga Birgi, who has also organized this webinar. Many thanks, Olga, for putting together an interesting program. Olga will give you a quick overview on the RE4Industry project, and Olga, I will invite you just to be as fast as possible, maybe
yes.
10 minutes just to give the participants kind of the framework of the RE4Industry project.
Okay.
Many thanks.
It will be my aim. Yes, I will try to not to be so boring.
Thank you.
Okay. Just a second. Can you see my presentation?
Yes, but
yes, we can.
And not in presentation mode yet here.
Yes, not yet. Now it should be fine.
Now it's fine. Please start, Olga.
Yes. Hello, everyone. Again, I'm going to give a quick review about our project RE4Industry. RE4Industry is an abbreviation. The long name of the project is the 100% renewable energies for industries. This is the aim of this project. And here you can see RE4Industry at a glance. We have 11 partners in the project consortium from 6 countries, which is including Belgium, Germany, Spain, Greece, Netherlands, and Austria. Our project coordinator is Fundación Circe from Spain. Alessandro is also a member of this association. And our project actually started on 1st of September 2020, and it's going to last for 3 years. We have less than 1 year until the project will come to an end. And the type of the project is a coordination and support actions project. Here you can see our project consortium more in detail. We have 3 different categories for the partners. We have technological and social experts, where Circe, BTG, CERT, WIP Renewable Energies, also White Research members of. We have renewable energy-oriented associations like Bioenergy Europe, Energy Efficiency in Industrial Processes, European Sustainable Energy Innovation Alliance, and we also have energy-intensive industries in our consortium. We have a steel producer from Spain, which is called Snedor, aluminium producer from Greece called Mytilenios, and a lactic acid producer, chemical company Corbinion from Netherlands. It's important that we have this energy-intensive industries in our consortium as well, because we have then first-hand view, and we will get to discuss with them and see which technologies are more suitable for them. And to give a little bit of context, as most of you would know, the European Union has started a progressive decarbonization with the aim to become carbon neutral by 2050. And energy-intensive industries are actually a really important part of this transition, as they represent 24% of the final energy consumption. That's why there is a need of a clear long-term vision and strategy in order to remain competitive while contributing to the decarbonization targets of the European Union. You can see some of the goals of the project. I will only name a couple of them, which are really important. The project is really special because we are trying to set a multi-actor collaborative network involved and actively compromised together and identify the needs of the sector in order to make possible this transition. What we are trying to do is that we are trying to initiate a stakeholder dialogue where every stakeholder will take place and help us with this decarbonization goals. Here you can see the general project workflow. Like other Horizon 2020 project, our projects is also being consist of different work packages, different activities and tasks are being involved in these work packages. I'm going to give you more detail about our technical tasks in the following slides. As I mentioned, what is important about our project is that we have a collaborative network which is being formed by the national level and European level experts. We have technical and policy experts, and it's important to have them to show our project results, project progress, and also get their ideas. What else we are doing is that we are looking at the status of the energy intensive industries on country level, on Germany, Spain, Netherlands, Greece level, also for the European level. And we are looking into the best practices for renewable energy integration in energy intensive industries. Here you can see a graph of different energy intensive industries and their carbon dioxide emissions as well as their energy consumption by the industry. When we look at the left side of the graph, we can see the megaton carbon dioxide emission equivalent of different industry. As we can see, iron and steel, chemicals and plastics, cements are one of the ones that have the most emission. And when we look at the glass, actually glass is not emitting as many carbon emissions as the other energy intensive industries. But when we look at the right side of the graph, we can see the energy consumption by the industry. Here, chemical and petrochemical is again consuming a lot of energy. And in the second place, there is non-metallic minerals, which are actually sand, gravel, limestone, and fertilizer minerals. They are best known for the production of cement, ceramics, glass, and lime production. Another outcome of the analysis on the status of the energy European Union industry. Here you can see the 4 different industries. Non-metallic minerals, when sand and gravel are also a part of, chemical and petrochemical, iron and steel, and non-ferrous metals. You can see some similarities and differences in these graphs. We can see that all of the industries are using electricity. Some of them are using it for a greater extent, like non-ferrous metals. Some of them are using it less, like non-metallic minerals. And when we look at the natural gas, it's actually a really significant amount of natural gases being used by all the industries. It's all around 30%, but we are also seeing that these industries have a great aim to lessen this natural gas consumption because of the war and also the energy crisis and increase in energy cost as well. We see oil and petroleum products are still being used by non-metallic minerals and chemical and petrochemical industries. And when we look at renewables and waste, actually, we don't see them so often. Only a small part is being used in chemical and petrochemical industry. And 13% is used in the non-metallic minerals. It should be another aim. If you want to achieve our decarbonization goals, we have to be integrating renewables more in this sense. And other activities we are carrying out is that we are looking at these case studies, the energy intensive industries, which are in the project consortium as well. We are looking at the innovative solutions for the renewable energy adaptation in these energy intensive industries. Here you can see our case studies, Nador-Corby and Mytilinios. What we are looking into is that instead of normal electricity, we want to get electricity from the green waste, like power purchase agreements, photovoltaics, etc. instead of natural gas, we aim to replace it with biomethane or green hydrogen. Instead of coal, biocar, even though it has lower efficiency, and instead of steam, electric boiler. And we are also looking at the short and long-term innovative energy solutions. We are developing roadmaps for full energy-intensive industries decarbonization through the renewable energies. Short-term vision is for 2030 and long-term vision is for 2050. We are looking into the technology options, achievable rates, as well as current sector needs. As you can see it here, for the heat production, we are looking into solar thermal, heat pumps, geothermal, biomass, biofuels, and green hydrogen. We are also producing different reports about all this single technology, which you can also find it on our project website later on. And for the electricity, we are looking into options like photovoltaics, wind, hydraulic, and power purchase agreements. And here I'm going to recap our RE4Industry actions really quick. We are aiming to have a strong engagement strategy following a multi-actor approach, also starting a dialogue with and within energy-intensive industries and energy-intensive industry organizations. We are also having a thoughtful review of renewable energy technologies and options for a 100% renewable energy production by 2050. Also insights into industry retrofitting, and we are producing recommendations. We are carrying out multiplication and replication tasks, and we are disseminating our results, and we have a solid communication strategy. That was all from my side. Thank you for listening. If you have any questions, I would like to take, or we can directly continue with the interesting part.
Now, Olgo, many thanks for giving an overview on the project, which was certainly interesting, and I can just reconfirm that both, like, you will find the results of the project, including interesting reports about a number of renewable energy solutions for energy-intensive industries on the project website, which is indicated on the slide. And we also much appreciate your involvement in the number of working groups that exist within the RE4Industry project. So if anyone who is not yet part of one of the working groups would be interested, just get in contact with us. Many thanks, Olgo, again. Very nice overview. And we will proceed with the program. And I would like to invite Christiane Nelles from BV Glas to give her a presentation. Olgo, I think you need to stop. Yeah, okay, perfect. Christiane, we can see your presentation.
Oh, it was, yeah, you saw the presentation, but I put myself on mute. Classic mistake. Okay. So thank you everyone for joining today. Olgo, I think we're a little bit behind on time. When was I supposed to stop? So what's the slide for?
No, we are perfectly, Christiane,
we are perfectly in time. Okay.
Yes, you have 15 minutes, okay. And if you're fast, we have some questions. Some time for questions.
Yeah, sometimes for questions and some maybe more sometime for the technical issues. So hello everyone. Thank you very much. I'm really glad to be here. I think for decarbonization, we need to not go on one path, but we need to look into all directions. May it be H2, may it be solar power, which for glass industry, which needs very high temperatures. I'm excited to learn more about maybe or geothermal power options for glass industry at some time. Right now, we are looking also on BV Glas in our project High Glass into the options for H2 admixture into the process gas, and we also Hendrik contacted me a long time ago talking about biomass for the glass industry, and I said, well, usually we use gas, but maybe we will try to find a way to turn the sustainable biomass into gas, which we then could use again for the glass production. So I think we have to look into all possible ways, also syngas or SNG, because we will need a lot of green energy. We will need it at all over Europe, at all the factories, and maybe you're lucky and you have an H2 grid next to your installation, but maybe not. And there's also different kinds of glass and different sectors, and so we are very open to explore all the green energy and especially all the green gas, the syngas that will be there for us to use in the future. And the urge to use less natural gas became even more important over the last year. So we're the national, so now okay, I will do it this way. We're the National Association for the German glass industry, representing all the sectors: flat glass, container glass, special glass, tableware, water glass, and processing and finishing. This is our team. I'm the advisor for energy and climate. We're also really active in environment policy, product policy, and also statistics. This I will maybe skip the data, but I'm sure we can send around the presentations later on, so you could have a closer look. All this information you will also find on our website. The German glass industry is the biggest in Europe, and we're actually in North Rhine-Westphalia, located not in Berlin. We have a small office in Berlin, which is also one of the hotspots for glass melting in Germany. Although I think you also put the spotlight on the final energy consumption. There you can see that especially in the glass industry, you use a lot of natural gas. It's like almost 80% of the final energy used is natural gas. So it's a big part that needs to be decarbonized. There, as I mentioned before, there will be electrification, there will be hydrogen, there will be syngas, there will be all the options that need to be explored to make this gray part then into a green part as we move onwards to 2045. The reduction of the specific energy consumption has declined over the last decade. So, in point of energy efficiency, we're still working on energy efficiency. BV Glas itself is leading some energy efficiency networks. We're supporting the national initiative of energy efficiency, but we also need, what we do need to focus right now is decarbonizing the energy we are using. I'm not sure if I should give you a quick overview of the glass manufacturing, because we have so many experts around here on the table. So just for maybe a quick close-up, we have the glass oven where the raw material and the recycled glass cullets are being molten, using up the most part of the energy. Gas-fired furnaces with electrical boosting are right now the standard. In some cases, for special glass industry or some smaller flaconnage production, there are also full electric furnaces. but using full electric furnaces is not possible for every kind of glass and not for all the sectors, because for example, if you take a large flat glass tank which produces up to, let's say, 500, 700 tons of glass a day, you have to have a very high quality of the glass, and therefore the chemical process needs to be also supported by very high energy input, and the glass has to be really clear, and so it's not possible or today to build full electric glass furnaces which melt over 200 tons a day. So, and there are some kinds of glass that are not so good for full electric melting than other kinds of glass. Then you have also the glass tank, you have the combustion process, but then you also have the cooling of the glass, the cooling layers, which are actually not cooling like a refrigerator, but you have the very hot glass, which has to be decline the temperature in a very stable and very technically overlooked process for the glass quality to be good and the product to be to have the quality that you need. Basically, you have the very high temperatures up to 1400 Celsius, or in some cases even higher, 1600 degrees Celsius. And then you also have the temperature declining up to the end of the line. Usage of waste heat is standard in the glass industry. So the waste heat you are using again to preheat the air for the combustion. And then again, you may have some waste heat with the temperatures are lower to dry the raw material or to use in your factory, probably for heating some other installations, or for your buildings where you have the people working, or for the office spaces. So green energy for the glass industry. I already mentioned that we have to look in all possible directions, and that we definitely next to using more green electricity also have a part of the high temperature processes that will need a green gas for the production of the glass. And here I just showed a chart. It's actually from another project, from the project High Glass, just showing the figures. It's right now you see the H2 admixture rate, but of course you could take a sustainable gas also in exchange for the natural gas, lowering the CO2 output of the glass industry. In Germany, we're using right now 16 terawatt hours of natural gas and emitting 4 million tons of CO2, just for the overview for the German glass industry. So thank you very much for listening. I'm very excited, but what the experts, the technical experts will say, because what we need in the glass industry is a very stable gas. So because the chemical and physical process of the glass melting is highly sensible, what the people in the factory do not want is like a gas that where the which is changing every few hours or every few days, so you do not get the optimal quality. It's it's a highly efficient process. So what you need is a stable, predictable glass to make the best quality glass that you can have for also the energy transitions, for high insulating glass, and good products also to run the oven in a very energy efficient way. You need a very stable gas to support all the technical features you have. And I'm very happy to hear all your technical discussions and input on that. Thank you very much.
Many thanks, Christiane, and thanks also for highlighting. I believe the requirements on quality and purity of syngas are probably highest in the glass industry, even compared to other energy-intensive industries. We will proceed with the presentation by Hendrik Steinort from Enviva, who will talk about green carbon security, cross-sectoral bio-based defossilization of hard-to-abate industries. Hendrik, the floor is yours.
Perfect. Thank you very much. Can you see the PowerPoint presentation?
Yes, all fine.
Perfect. Thank you very much for the invitation. It's very interesting to see the entire value chain that ought to be necessary to defossilize the glass industries assembled here. And my approach is to represent a little bit the first step of the value chain, namely where do we get the sustainable biogenic carbon material that is necessary in order to drive the bio-based defossilization of hard-to-abate industries. And I'm starting with representing a little bit the company that I stand for. My name is Hendrik Steinort. I work for Enviva Inc. That's the biggest producer of industrial wood pellets in the world. We're currently producing 6.2 million tons of industrial wood pellets. Just as a comparison, Germany, the biggest producer in Europe, is currently producing 3 million tons. So about 50% of the total volume that we produce on an annual level. And we're going to expand the production of industrial wood pellets to approximately 12 to 13 million tons in the next 5 to 6 years. We have deep water ports in the Atlantic and in the Gulf, and we mostly transport the industrial wood pellets in Handymax and Supramax sized vessels to Europe and East Asia. And why we are also interested in looking at these kind of value chains, we're looking at fossil-based value chains, for example, would function mostly on the basis of natural gas, or on coal, or on other fossil-based materials, and try to convert them, transform them into bio-based value chains. This is why we're looking at power and heat. Of course, that's a key sector, but also hard-to-abate industries. We're trying to bring technology providers together with industries and try to not just provide one level, namely the feedstock level, not just one level, the customer level, but try to assemble the entire value chain in order to drive innovations, in order to look at certain strategies to defossilize the sectors. And then, of course, underwriting all of these for the biogenic carbon resources that we offer is sustainability. With it, everything stands and falls. And in order to understand a little bit where the wood comes from, it's the southeast of the US. The forestry area is 1.1 million square kilometers. That is probably 3 to 4 times the entire land size of Germany. And the forestry inventory in the southeast of the US is growing by 350 million cubic meters a year. So it's a sustainable forest basin that accounts for 1/5 of the entire sawmill industry in the world. And the long-term sustainable supply is now the next topic. I think it's very crucial now to understand how can we leverage biogenic carbon resources in order to be able to defossilize industries that need it the most. And here we have worked together with Agora Industry on creating a climate positive chemical industry. And we've looked at biogenic carbon potentials. And the left image you will see on the x-axis, you have the demand from very cheap to very costly. And then on the y-axis, you have low supply and high supply. And we are approximately in the top left corner with forest waste, forest residues. We're not driving forestry decisions, but we are assembling and aggregating the forest residues that can't be used by the sawmill industry. And therefore, we have a high supply scenario with a very, very low cost position. And that's obviously perfect to utilize for defossilizing industries. Then we have set different priority criteria on how should we use biogenic carbon. And the first is, of course, optimization of recycling rate. What is the existing biogenic carbon in the value streams in a particular industry? And then in the end, we can use the biogenic carbon capture and storage and utilization in order to use maybe the residual carbon streams such as CO2 in order to use them for higher value applications, for example, in syngas. Then the priority 2 use of biogenic C sources. There's a lot of regional biogenic C that is either untapped or has been used for lower value applications. We have to mobilize them in order to fulfill the requirements of this industry. And then priority 3, PTX, power to X with domestic and global C sources. That means we have to look for PTX solutions that will in the end also require biogenic CO2 in order to create important higher value platform chemicals, for example. And then priority 4, the most important, we can't sustain the demand that is being leveraged on biomolecules in the industry in Germany, but we also have to look at a stable long-term security of supply of biogenic C. And in order to understand how what are the challenges for Germany, talking about the enabling of a circular bioeconomy, we have to look at production strategies. How do we produce in a sustainable way the volumes that are necessary for these industries? Environmental sustainability, that is a little bit needs to be framed in how do we accord to the sustainability standards that are necessary to increase the stock or inventory of the LULUCF, and at the same time provide a sustainability. That provide a sustainability framework that enables investor security as well, because nobody wants to invest for 2 or 3 years and then suddenly all of these requirements and regulations do change. But you need 5, 10, 15 years in order to provide a business model that works and that can be scaled. And then, of course, transnational import strategies. We have talked about hydrogen before. Hydrogen is a key material for the energy transition and for the industry transition, but there are other strategic industry transition materials and resources such as biomass, such as biogenic C, and we also have to look at it. And we've seen that a lot of the global partners, have not been reliable suppliers of either natural gas or other commodities. And then we go for on the topic of Germany. What are the theoretical biomass potentials? They're really huge in Germany. 236 million tons. Just for reference, we have approximately 450 to 500 million tons of embedded carbon in our global industries per year. But of course, this all goes down to the equivalent of 29.3 million tons of mobilizable technical biomass potential. Those are numbers which the VCI together with the DBFZ has set up. And the range is approximately 12.8 to 45 million tons per year. And then how does it compare to the demand that the industry in Germany has? The demand alone in the chemical industry amounts to approximately 26 to 13 million tons of biogenic carbon. Biogenic carbon means you have to take biomass with a factor of 0.5, because 1 ton of biomass has approximately 0.5 tons of carbon, and therefore we might be or struggling with a gap of approximately 20 million tons of biogenic carbon starting in 2026. So we have to look a little bit abroad in order to understand that the industry defossilization and a pure green economy can't be sustained just by utilizing regional resources. Then I want to go quickly to the actual use case of these biogenic carbon resources. in the form of bio to X. We have biogenic carbon, and we transform it to X. For example, syngas for heat processes in the glass industry. And here we have basically the climate champion wood pellet. It's a defossilization platform. It has zero carbon cost. It has a very homogeneous quality. It can be used for process temperatures up to 1,600 degrees, and it is available at scale globally, 50 million tons with an upward trajectory in the next years. And then the biogenic carbon can be used as a green carbon source for biopolymers, for green heat, syngas, biomethane, bio-SNG for the glass industry, green hydrogen, but also for biomethanol. And what are the strengths of, apart from those which I just mentioned? We all understand that we're in a carbon-constrained world, and the carbon-intensive economy will not go away. Decarbonization is looking at probably more the energy sector, but we need for all of these industries a strong carbon basis that is regenerative, renewable, and sustainable. And the fossil infrastructures, for example, in the glass industry, in the ceramics industry, but also in the cement and lime industry, but also in the steel industry, they can be, if these technology pathways are scaled up, they can be recycled. There can be low cost, low capex implementation of renewable infrastructures in formerly fossil infrastructures. And we also can use hybrid systems where we have natural gas and mix it with syngas, for example, derived from biomass gasification. And then one very crucial thing for capex investments and long-term OPEX is, of course, investor security. And investor security can just be achieved if you have a global supply that is reliable and long-term, and maybe even to a fixed price. And then, of course, sustainability remains at the heart of the transformation. We can't go beyond the criteria that are going to be set out by RED3. And here we have another overview of what wood pellets as a defossilization platform can be. For us, relevant is syngas. It can be used as a process heat reducing agent, but it can also be used as a precursor for other higher value chemical platforms. There we have 10 to 12 gigajoules per non-cubic meter. And what is crucial is that for 1 kilogram of wood pellets, most probably depends on the process. These are all dependent on the processes that you use. You can probably produce 2.4 kilograms of syngas. So that's probably in order to understand the scale a little bit. And then now we go for scalable biomass gasification. It is probably a very, very interesting modality to defossilize potentially the glass industry. It can be used cross-sectoral, not only in the glass industries. There are a lot of symmetries in other industries like the ceramics industries, but also lime, steel, and cement industry. And we can either look at an approach where we see that the gasification is going to be used in-house. We're going to create value in-house, or on the basis of a contracting model where you're going to take in external expertise, and that will obviously accelerate the transformation process, while at the same time also look at future applications of that process in these industries. That's also coupled with HR expertise transfer and professionalization of these industries. And then we have different technologies on the market, fixed bed gasifiers, we have fluidized bed gasifiers. Later we will hear some of these technologies and how we can possibly use them. We have biomass gasification is more efficient than fermentation because you can scale it and it's immediate. Fermentation as a process to produce biomethane is obviously an established process, but if you really want to scale it for a given industry, then you need to understand that biomass gasification is the fastest pathway to having scalable amounts of syngas that can be used, either upgraded to bio-SNG or biomethane as an equivalent to natural gas. And therefore, we need to have a value chain that is established and can provide long-term security of supply of syngas. Then, of course, in the status quo, these are all the different sectors where syngas potentially can go. But at the same time, what we are focusing is green process heat for the defossilization of energy-intensive processes. not only ceramics and glass, but also pulp, tile, sugar, and asphalt industry, of course. And then last but not least, at the very tail end of this process, if you have biogenic CO2, renewable CO2 coming out of the process, if you capture it in the end, then the glass industry in some way or another can become a climate positive industry. And I think what we are seeing now in 2045, Germany will be climate neutral. What we need until then will be negative emissions, because there are some emissions that we can't easily abate. So that's also something to be kept in mind. Why biogenic CO2 does also on the end of the process generate additional value for these industries. And then sustainability, the most crucial aspect of this value chain proposal. Here, the biomass that would be provided from different providers can rely on sustainability criteria such as FSC, PEFC, Sustainable Forestry Initiative, SBP as well, Sustainable Biomass Program, or the Tree Farm certification scheme. And we at Enviva have a responsible sourcing policy that can only source from growing forests. Track and trace, you can trace back with a satellite-based GPS system every ton of wood that is delivered to you to the plot where it was harvested. And then we also have a fund for high biodiversity plots, and we contribute to reforestation actively there. And that's me. I'm happy to talk with anyone who's interested. Please reach me under that email address. And thank you very much for the opportunity.
Yeah, many thanks, Hendrik. If you allow, I would have one question to you, which actually concerns the current development on European level on the sustainability aspects, namely the discussions towards RE3. Like, this will be not new to you, of course. The keyword is this primary biomass issue. Would you be bold enough to say a few words there? Do you let's say, how is your approach? Like, it might affect your business model, no?
Yeah, that's a very very actual question. So I could go now into the details. I think I'm going to look at the meta level. The meta level says that 80% of the renewable heat that is currently being produced in the European Union is being derived from biomass. 50% of that is being derived from primary woody biomass. If they would get rid of it in the next 2 years, then there would not be any renewable heat for Europe. And what we've seen in the difference between the position of the Commission, which was quite in favor of the status quo in RED2, is that the European Parliament followed more or less the recommendations set out in the ENVI committee that later went into a discussion with different committees in the European Parliament. And the European Parliament in the end decided that they would go for a vastly de-radicalized version of the ENVI committee's proposal. So that we are now at a comfortable level where we see that the primary biomass is definitely going to be counted as zero in the EU ETS, and is further going to play a massive role in the renewable energy expansion in the European Union. And what we are also going to see is that while they're going to enter into the trilogue discussions towards the end of this year with the Council, the position will probably return to its more conservative and forward-looking position on primary woody biomass that has been laid out in the RED2.
Okay.
So that's...
Yeah, many thanks for this insight, and I share your hopes that that the policy making will not again cause insecurity towards the value chains you've already mentioned in your talk. Okay, many thanks again. We'll proceed with the next presentation. I'm happy to invite Dr. Jörg Leicher from the Gas and Wärme Institute Essen, who will talk about combustion of hydrogen and raw biogas production from fermentation processes. Dr. Leicher, the floor is yours.
Yeah, thanks. I hope you can see my slides already. And now also in the presentation mode. Great.
Exactly.
So thank you very much for the invitation. Good afternoon, everybody. So I want to talk a little bit more about the technical issues of switching from a conventional fuel like natural gas to something new and decarbonized or partially decarbonized, like hydrogen natural gas blends or pure hydrogen, or also to some degree I'll be talking a little bit about raw biogas, so biogas from fermentation processes for decarbonization in the glass industry. I have to admit, I thought I had a little bit more time, so I have a little bit, a few slides too many. I'm going to rush through them. I think this is something that we already talked about. So obviously we need to decarbonize not only the power grid and the mobility sector, but also industry, because industry makes up a very significant part of our energy consumption. So in Germany, it's about 30% of the final energy consumption that is accounted for by industry. And actually 2/3 of these 30% is actually process heat. So this is process heating is the most important aspect when it comes to decarbonizing energy in the industrial sector. And of course, we have to look at primarily at high temperature processes. And we have different options. We could go for electrification with green power. If that's available, that's certainly one option. If it's technologically feasible, we could do some kind of CCUS, so carbon capture and storage, or carbon capture and utilization. We can think about biogas or biomethane or syngas or synthetic natural gas, whatever, or we could go for hydrogen. And especially if you follow the media in the last few years, hydrogen has gotten a lot of traction here, with many nations, many organizations publishing their own hydrogen strategies. And this is to some degree also driven by the European gas industry, which is moving forward with plans to inject hydrogen directly into natural gas grids. So even if you as a company, as an operator of some heat equipment, say, I don't care about decarbonization at all, as long as you're connected to the gas grid at some point in the not too distant future, you will have to think about at least natural gas hydrogen blends. But of course, they are also looking a little bit further into the future by looking at dedicated hydrogen pipelines. And this is something that basically all energy intensive industries have to think about, and so the glass industry does as well. I want to talk about primarily a project called HyGlass, which was already mentioned by Christiane a few minutes ago. And this was a project where we as GWI partnered with BV Glas to look into the potential of hydrogen for glass manufacturing in North Rhine-Westphalia. For those of you who are maybe not familiar with the German political landscape, North Rhine-Westphalia is one of the major federal states in Germany. It's the most populous state. It's also one of the industrial heartlands of Germany, and especially when it comes to the glass industry. And we were looking at options here for glass manufacturing sites in North Rhine-Westphalia to use hydrogen up to 100%. So we were talking about blends, but also pure hydrogen. And we wanted to see what would the impact be if we start introducing hydrogen, if we start switching to alternative fuels, but on a mostly technical level. So we looked into the manufacturing process itself in terms of efficiency, heat transfer, pollutants. There are other pollutants out there except for just CO2. So the glass industry still has to think about NOx emissions, for example. Glass quality, obviously an issue, but also economic considerations, things like security of supply. I mean, this is something that we've heard more and more in the last few months due to the developments in Ukraine. There are things to consider. You cannot simply switch off a glass melting furnace just because you don't have any gas or electricity. It will take damage. So security of supply is certainly an issue here. And this is also something to take into account when you switch to renewable energy sources. What we also wanted to do was we wanted to transfer to real life plants based on information that we got from computer simulations and also from semi-industrial test rigs. So we ran a lot of experiments, and what we also did was what's called a GIS analysis. So we looked at geographic data to look at various scenarios for hydrogen for glass manufacturers in North Rhine-Westphalia. I will skip over this. This has already been explained. So we do have many different combustion processes, also many different combustion technologies here. So a glass melting furnace will behave differently when it comes to hydrogen than, for example, a feeder or an annealing layer. So this is something that we have to take into account. And of course, we have to take the quality of the fuel into account. Hydrogen and natural gas are very different fuels. You can see that if you, for example, look at the calorific value of hydrogen is about 1/3 of the calorific value of natural gas, which means you need about 3 times the higher volume flows to produce the same amount of heat. At the same time, we have a reduction in the minimum air requirement. What it means is the flow patterns in the combustion chamber change, mixing of fuel and oxidizer changes, the flame changes, the heat transfer changes. We have other aspects. A hydrogen flame with air is significantly hotter than a natural gas flame. So we have to think about NOx emissions, for example. That's the bad news. We have to expect higher NOx formation. The good news is it's still the same formation mechanism. So we can use many of the technologies that were developed over the years to reduce NOx formation in natural gas combustion and can apply them to hydrogen combustion or to the combustion of blends. So we don't have to reinvent the wheel here, but this is something that we have to keep an eye on. The laminar combustion velocity, this is SL. This is something that's actually only relevant for the premix burner. So this is something that we have to think about in feeder systems in the context of the glass industry, but it's actually less relevant for the melting furnace, which is good news because if you look at the numbers, there are significant differences here. So this is really something to keep an eye on. But for the melting furnace, which is the biggest part in terms of CO2 emissions, in terms of energy consumption, this is actually less of a concern. Yeah, and of course, we have to think about CO2 emissions. You can calculate if you burn methane to produce 1 megajoule of heat, you will produce 55 grams of CO2. That's chemistry. That's nothing you can do about it. If we look at these plants today to go for maybe 20% volume percent of hydrogen in natural gas, that means we have a reduction per megajoule of about 7%. Not that great on first sight. But if you think about all the gas that we're using in Europe, and this is something that we could do without having to modify hardware, all the 200+ million appliances all over Europe, this is something that we could do quite quickly. But of course, in the long run, you have to think about going for pure hydrogen, and it should be green hydrogen because otherwise you're just shifting the emissions elsewhere and you're not doing the climate any favors. So what we did in our project was we did a lot of testing, a lot of experimentation on semi-industrial test rigs. This is one of our test rigs that we used for high temperature combustion investigations. It's definitely smaller than a real life glass melting furnace, but it's in terms of its operational conditions, it is actually quite similar. So we can have firing rates here up to 1.2 megawatt. The biggest glass melting furnaces that I know go maybe up to 100 megawatts. So there's of course still a scale issue here, but it's better than a lab scale experiment. What we can do here is we can provide air preheating up to 1250 degrees. So that's reasonably close to what you'd see in a regenerative glass melting furnace. We can achieve furnace temperatures up to 1600 degrees, which is also what you'd find in a real live glass melting furnace. And what we can do here, we can go to hydrogen levels of up to basically 1 megawatt of firing rate. So we could operate this furnace with pure hydrogen at all alone. We also did melting experiments. So we melted glass samples of different qualities to see how they are affected by the change in the combustion process. Because at the end of the day, as a glass manufacturer, your primary focus is not decarbonization. Your primary focus is to produce glass to a given quality. And decarbonization is just an additional complication in your daily work. So they want to know if they switch from natural gas to hydrogen or to biogas or whatever, they want to know that in the end, how will this affect their product and what can they do to maintain the quality that they have to. We ran a number of measurement campaigns. So this is some impressions of our first measurement campaign in December. One of the things that people often forget is how logistically challenging it can be to run large-scale experiments with hydrogen, because you have to have a lot of hydrogen, so it's going to be expensive. You need to have the trailers on site. We ran experiments for firing rate of 500 kilowatts with an air access ratio of 1.1 and an air preheat of 1150 degrees. So that's basically what you see in a regenerative glass melting furnace. Our furnace is quite flexible, so we were able to recreate an underport configuration, which is typical for such furnaces. It's also something that you only find in the glass industry. So that's also something to keep in mind. Process industries are very, very different. So furnace types that you see in the aluminum industry are probably not something that you'll find in the glass industry, and vice versa. And if you talk to ceramics, again, they will have different technologies there. So that's also something to keep an eye on. But in this context, we were able to really recreate a regenerative glass melting furnace conditions, and we ran 2D field measurements, and also we tested different control scenarios. These are just some impressions from the inside of our furnace. And what's interesting here, I don't want to go into the specifics, but one thing that which is kind of obvious is a hydrogen flame is basically transparent, at least in a hot environment. And this has consequences because it means that heat transfer takes place in different spectra. Depending on what you're producing, this may or may not be an issue. Actually, in a cold condition, hydrogen flame is reddish. But if you look in a hot environment like here with the refractory in the background glowing, then basically the hydrogen flame is almost invisible. At least on the naked eye, you have, of course, radiation in the infrared spectrum and in the UV spectrum. We carried out measurements. These are temperature measurements from the horizontal burner plane. And this looks a little bit weird at first sight because it seems as if hydrogen flames with higher level of hydrogen, we have a reduction in temperature, which is unexpected. But the reason for this is that this flame is moving out of the measurement plane. So we don't catch the maximum temperatures anymore in the horizontal burner plane, but we do know that the hydrogen flame is actually hotter because we can see that from the flue gas emissions. So these are measurements from the flue gas, basically from the chimney. So you can see we kept the air access ratio constant, we kept the furnace temperature constant by varying the heat load. And first of all, what you can see is with increasing levels of hydrogen, we have a reduction in CO2 concentration, which is kind of the point. And so decarbonization by hydrogen works. But what we also see is we have an increase in NOx emissions. And this is something that was expected. And this is also something which shows us that we have an increase somewhere in the furnace of local higher temperatures, because otherwise we wouldn't see this increase in NOx. We did melting experiments. This is the small test rig that we use for that. So we are able to introduce samples of different glass qualities into the running furnace to do melting experiments. We had our colleagues from HVG analyze the glass samples. I am not going to go into detail here because this is really not my area of expertise. For me, glass material science is basically black magic or alchemy or whatever. But there are effects there which were expected. You can see that with different levels of hydrogen, we see some changes in the color. This is not unexpected. This is something that we can probably deal with. What was also interesting was that we saw some increased soot formation in some levels of hydrogen, which is something that we cannot yet explain, but it's also something that that other people saw, so we're not the only ones there. And we did computer simulations to transfer this knowledge to real-life furnaces. So this is a computer simulation of a real-life glass melting furnace. This is a furnace that's actually located in southern Germany. So obviously a little bit bigger in terms of firing rate, 12 megawatts. But you can see also that here, if you keep the firing rate, the access ratio constant, also the air preheat temperature constant, then for the impact on the temperature distribution in the furnace is relatively similar. We have, of course, still have higher maximum temperatures, but overall you can do a lot with combustion control here. We can see that as well if we look when we look at the heat transfer impact factor. That's basically the heat transfer going into the heat going into the glass melt compared to the reference case, which is the case with natural gas. You can see that here we have relatively stable heat transfer going into the glass melt. We still have the slight increase in NOx emissions, so this is something that we have to keep an eye on, but this is technologically manageable. And last but not least, in the context of hydrogen, we also looked at the question of supply, because at the end of the day, these systems have to be supplied with energy. You cannot simply switch off a glass melting furnace. So we use GIS, Geographic Information Systems, to look at 9 locations in North Rhine-Westphalia where there are glass manufacturing companies. And then we looked at the vicinity in terms of what's there in terms of wind turbines, in terms of PV panels. We looked at different distances, 10 and 20 kilometers, and we very optimistically assumed that these wind turbines, these PV panels, are only there to produce electricity for us to produce hydrogen, which is of course a little bit naive, but it gives us the very first assumption. And even with this very optimistic assumption, we saw that with one exception, the local potential for hydrogen production just isn't there to significantly substitute for natural gas. And that's an important point here. When we talk about energy intensive industries, we will need some kind of green infrastructure, be a green power grid or a dedicated hydrogen grid, in order to provide the amounts of energy that we need and to do so reliably. So that's really something, one of the main findings of this project. Infrastructure really is important here in order to decarbonize energy intensive industries. And last but not least, because I've been asked to talk a little bit about biogas, we also did a project on the use of biogas from fermentation processes in the context of natural gas, in the context of decarbonizing the glass industry. So if you look at biogas, it really depends on the process that you're using. It depends on the feedstock that you're using. It is obviously quite different from natural gas, and this is what this table is supposed to show here. And in principle, you have two main concerns. First of all, we have the main properties changing, like the calorific value, Wobbe index, density, things like that, which will have an impact on the flow field, on the mixing, on the actual combustion process, on heat transfer. And then we have also trace components, like ammonia, for example, or H2S or something, which means we have to think about pollutants like SOx, NOx, things like that, but also potentially interaction with the glass melt. So we had a project, or actually two projects, called Biogas Glass 1 and 2, where we with a few partners, HVG, which is the German Association of the Glass Industry, FGF, which is an association for refractory materials, and also with Verallia, which is a glass manufacturer. So we wanted to see if it's possible to use raw biogas, so not upgraded biomethane, but really raw biogas for glass melting, both on a technological and economical level. We had two projects. The first one looked into more fundamental aspects, and then in the second part, we actually implemented this. So we used a real-life, medium-sized regenerative glass melting furnace. We connected it to biogas plant, and we're able to supply about 30% of the energy demand from this biogas plant. We were lucky because there was Verallia had a smallish glass melting furnace right next to a biogas plant. And so we were able to just build a small pipeline to connect the biogas plant directly to the furnace in order to provide this energy. You can see from the CO2 balance, of course, it works. So,
Dr. Leicher, we are running a little short of time. Sorry for that.
I'll skip over this. So obviously, but you have to take a few things into account. You lose a little bit of efficiency here. And overall, to come to a conclusion, yes, we have to think about decarbonizing, especially high temperature process heat. Hydrogen is an option here. Biogas could be an option here. There will not be one size fits all solution. We will really need to look at local situation. We will need to look at security of supply. It is doable. I think technologically, you can use hydrogen. You can use hydrogen natural gas blends. You can use biogas or syngas. On a technological level, a lot can be done. We have to think about, of course, about the origin of hydrogen. It doesn't make sense to use gray hydrogen for decarbonization. That doesn't just shifts the emissions. And when we think about biogas, it's also an option. We saw no negative impact on glass quality or also on the refractory, which is also a concern. This was confirmed by investigations in a real-life industrial site, but in the end, one bottleneck is really providing sufficient amounts of biogas. That's certainly an issue because, again, the amounts of energy that we need are substantial. And there are also some regulatory hurdles. In this context, it was, for example, that when they wanted to switch from research mode to normal operation mode, because they actually wanted to continue this injection of biogas, the authorities, local authorities, told them that they don't know how to handle that. They can handle pure biogas sites, they can handle pure natural gas sites, but if it's a mixed operation, they don't know how to do that. So they wanted to consider this like a municipal incineration plant, and that was the end of the game because that has all kinds of additional requirements. So there's also some bureaucratic aspects to deal with in this discussion. And I know I took a lot of time, but thank you very much anyway. And if you have questions, please, if we have the time now or you have my contact info here, I'll be happy to discuss this in way more detail. Thank you very much.
Thank you very much, Dr. Leicher. No, very, very interesting. would open the floor if there is any questions to Dr. Leicher at this stage. No, we said we would try to give the floor for some technical discussions. Are there any questions? Actually, from my side, I have two. These are not technical questions, but I would like to ask you why. What was the reason why you did not focus on biomethane instead of biogas? Yeah, okay. And then the second one is. Now we know that there is a sense of urgency, and you are looking at the issue from the technical side. However, the main bottleneck is the supply side. What is your feeling about the time frame? If we really put all the eggs in the baskets, and if we get together, when can this substitution take place?
So maybe to answer the first question, the simplest, more simple question first, the answer why we don't look at biomethane is simple. Biomethane has to be of comparable quality to natural gas. So if I burn biomethane or I burn natural gas, technology-wise, it's hardly any difference. There are some minute differences that you, in terms of maybe trace components or things like that. But if you have biomethane, it has to be of the same quality. It has to fulfill the same quality criteria as natural gas. Otherwise, you cannot inject it into the grid. And the idea was, if we can use raw biogas or roughly desulfurized biogas, we can skip over this energy-intensive part of actually upgrading the biogas. So that was sort of the idea. So what we looked at was really a blend of 50 to 70% methane, and the rest mostly CO2. And we wanted to see if this works, because biomethane is, from a combustion perspective, is basically natural gas. That's
a
kind
no-brainer, basically. Yeah. Okay.
Yeah. And the second question, yeah, that's to some degree this is a chicken and egg problem, because of course, if I as a glass manufacturer think about decarbonization, and we are involved in some of these projects as well. I have to, my first concern is really security of supply. So I have to be sure that if I switch to hydrogen or syngas or whatever, I have to be sure that for the next 15 years or so, I will have a sufficient amount of hydrogen or whatever available 24/7. And of course, so I sort of rely on an infrastructure, and at the same time, of course, the operators and owners of infrastructure say, okay, I will not create a new infrastructure unless I know I have a sufficient demand. So at the moment, this is really a chicken and egg problem. And of course, there's a lot of competition. I mean, hydrogen at the moment is a relatively rare commodity. We don't have the infrastructure yet to do it on a large scale. And there's a lot of competition. If you talk to the steel industry, they will tell you how much hydrogen they need. And if you do the calculation, you will see if they get all the hydrogen that they need, there will not be anything for everybody else. So that's also an issue. And it's the same, I guess, with biomass, or it's the same with syngas. So there's a competition, which is, of course, not good for the price of energy, which at the moment is high anyway. So I don't know, but it's something that will not. I don't think the market alone will regulate this. This will need some substantial startup support from the governments, from the European Union, in order to get this going, because we need these industries, we need the jobs, we need the materials. So we cannot have it all go to China, because it won't help on a global perspective anyway. But this is really something which will not be handled by the market itself.
Yeah, I agree. Thank you very much. We have a hand by Fabrice Rivet.
Yes, thank you, and thank you, Jörg, for the very interesting presentation. It was very, very quick, so it was not easy to catch everything. And I just would like to.
I had 25 minutes, and I saw I had 15, so I rushed it.
That's a challenge. But can we go back to the slide where you see the NOx emissions? I don't know if I saw correctly. Yeah, I think no, it's not this one.
That's not this one.
It's there. It's
this one.
lower. Yeah, so for the NOx, if I see correctly, you have a quite of maximum at 30% hydrogen, then it seems to go down, or is it stable? But at least you reach a plateau, or you even see a decrease after 30% hydrogen. Do you have any explanation for that, or there is a very sharp increase from 0 to 30,
yeah,
and
but
then?
The point is, we've been discussing this. So first of all, this burner was designed for natural gas, so it was in no way optimized for the blend.
Okay.
And also, we are lacking a few additional data points there. So this could be an outlier to some degree. The 30% could be a little bit high, could be an outlier, that it should be actually a little bit lower. But the overall trend makes a lot of sense because if you look at how NOx is formed, it's primarily dependent on temperature. We do know that hydrogen flames are simply hotter than natural gas flames, so it makes a lot of sense for NOx to increase with higher levels of hydrogen. That's the overall trend that we see. You see at the same time that we have a reduction in the CO2, in the CO. So that it sort of corresponds. So this, for me, means that maybe at this point we have some kind of instability in for this particular operational point. One thing that we have to keep in mind, and this is something that's not yet been included in this presentation, is the way that we measure NOx. Is we measure NOx dry. And of course, so we take a gas sample, we take out the water vapor from the combustion because the sensors cannot handle humidity, and then we measure the rest. And if you do this with hydrogen, you're at an inherent disadvantage because you produce more water vapor when you burn hydrogen than when you burn natural gas. So this is not, so you should compare this a little bit differently. You should look at NOx not in terms of ppm or milligram per cubic meter or something like that, but you should look at it in terms of milligram per megajoule. Because just by drying the sample, you're distorting the comparability. And
Yeah, I fully agree.
This is something that we need to look at, and also which has to be taken into account when we talk about the about NOx emissions, because it makes sense that hydrogen will produce more NOx than natural gas combustion simply because it's hotter. But if you want to quantify this, we need to rethink the way that we measure and evaluate emissions. And for example, if I compare here the case between pure natural gas and pure hydrogen, it's a difference in dry emissions of about 60%. So I go from 40 to 650 ppm. So that's a 60% increase roundabout. If I go for the wet emissions, which I can do the calculations, it's only an increase by 30%. But if I look at it in terms of energy in milligram per megajoule, it's only increased by 20%. So just by choosing the unit that I look at, I can distort the comparability quite a bit.
Mm-hmm.
And this is also something on a more regulatory issue level that we need to discuss, because we will have to think about NOx. Of course, we always have to think about NOx in high temperature applications. But if we do it the way that we're used to, then we are just exacerbating the issue. And not because it's physically relevant, but simply because of the way that we measure things. And that's also something, I know that the power plant industry is looking into this, the gas turbine people are looking into this, and this is something that we will need to do as well. Basically everywhere where NOx is an issue, we need to get away from these dry ppm concentrations or milligram per cubic meter, because this is an additional challenge which is physically not justified.
I fully understand, and that there is some artifact with wet or dry
Colleagues,
measurement.
I usually I would say you would need to discuss this in the coffee break. In this case,
There is no coffee break.
Yes, I would need to, you please try to solve it via emails after. Otherwise, the other speakers will not have sufficient time. I'm very sorry about that.
No,
Dr. Leicher, many thanks again. Sorry, try to follow up via email or in the chat. Many thanks. We will proceed with the next presentation. Dr. Ferdinand Düner from HVG-DGG. Dr. Düner will give a presentation on synthetic natural gas production from the exhaust gas of a container glass plant. Dr. Düner, the floor is yours.
Thank you. Okay, so I will show you a presentation which is mostly based on the presentation we gave on the ICG conference this year, where we proposed a carbon capture and utilization cycle in the container glass production. And you should be able to see my first slide now. And there you can see basically everything which is in our concept. That is, we produce container glass, that are the bottles on the bottom. And during container glass production, usually we get CO2, especially when you use we use combustion for energy generation or heat generation. So we want to use renewable hydrogen, which is made by electricity, and we want to produce e-fuel to have a cycle for CO2. In that way, we have a net production of e-fuel, and we do not have any further CO2 emissions because every carbon is captured. Okay, we means this is a project together HVG with the DLR, and we have a couple of partners, which is Schott, Ada Glas, and Linde. Yeah. So our main objective for our study is we want to show, is that possible? Can we combine these technologies? That means technology chains. Basically, we select the fitting technology chains, and we want to show some cost estimations. Of course, focused on the glass industry. And there are a couple of benefits. As I said, we have 0 CO2 emissions, and we have a fuel net production. This fuel net production comes because we have processed CO2 emissions. We use carbonates for glass production, and these carbonates have to be dealt with. Another benefit regarding the fuel is, of course, that we can store the fuel for emergencies like we have no electricity or whatever. We use only electricity for our modeling. That means we are only dependent on the raw materials for the glass production, that is colored and batch ingredients. And we have a modular build. So that means in theory, we could outsource the different parts of the model to different companies. Of course, we have a couple of drawbacks. With this attempt, we could also instead just burn hydrogen. With that, all these modular builds, we have a comparably low efficiency. It's a comparably high investment, and we have a high complexity. Okay, so I want to show you, guide you through the process that we imagined. That is, we all start everything with a glass furnace. The glass furnace produces a lot of CO2 and produces a lot of glass, and needs a lot of heat and has a lot of waste heat as a result. We assumed an oxy-fuel process, 300 tons glass production per day, and we assumed a heat recovery system, which is in the middle. And from the heat recovery system, we need to get the fuel first to heat the glass furnace. I will go backwards just in case if you wonder. So the fuel in this case, as a very first attempt for our calculation, is methane. Methane because it is the stuff the glass industry knows today. It is not the one and only solution, but it is the solution we have the most knowledge with. The methane will be synthesized by a tramp process that is, of course, an exothermic process. So we will also have to integrate that into the heat recovery system. And that process requires hydrogen that is produced by electrolyzer. In this case, we calculated everything with the PEM electrolyzer, and we need some CO2. The CO2 comes from the furnace, runs through a gas cleaning process, and we have a couple of stages. That is a wet scrubber. Please don't hurt me, glass industry people, because wet scrubbers are not very favorable. However, we need very, very low amounts of pollutants, and that is only possible with wet scrubbing in our first optimization. After that, we need some hydrogenation to get rid of further oxygen and some guard beds to reduce the levels of sulfates or sulfur and halogenides to about 10 ppb. We need these low levels to protect the catalysts, which we need for the fuel synthesis. So this is our setup that we want to talk about. Our general approach is we have 3 basis tools that we use. We use a Python simulation to assume the amounts of matter that flow around and the amount of heat. We use Aspen Plus for the process simulation, and the DLR has their own techno-economical analysis tool, which is called TEPIT. And this uses the input of Aspen Plus to estimate the cost of the different pieces in the setup. For the economic assessment, as I said, 300 tons of glass per day. We use methane as an e-fuel. And we calculated everything for the year 2020. 2020 is, in this case, the better option than 21 because the electricity pricings in 21 were, let's say, not very evenly spread. Of course, now the electricity prices are higher, so we have to recalculate everything for the next year, but we prefer to use the year 2022 for our next calculation step because this is, yeah, a more even approach. The glass furnace, of course, has to operate 24/7, 365, and we use an interest rate of 7%. The methanation plant does not need to operate the whole year, but we assumed 8,000 hours a year with an estimated plant lifetime of 30 years. That does include this does include the repairs, but it does not include the furnace itself. We excluded the furnace of the for the cost operation, cost estimation. In 2022 and 2020, we had an electricity price of approximately 42 cents euro per megawatt hour. Our supply was through the electricity grid. We had a backup system through the gas grid. Yeah. So now, if we look at the fixed capital investment cost that we estimated for this approach, we can see that we have approximately 100 million euro that are required to build that system in 2020. And this is quite a lot, and most of it is for the electrolyzer. All the stuff that we need for the glass, the glass production, the gas cleaning, that is comparably low. We need about 10, 12 million for wet scrubbers, and the rest is for the other cleaning parts. But the electrolyzer is the major point. And if we look at the net production cost, we can see that even the PEM module is not the most important part, but even more expensive is the electricity. So if we sum everything up, we can use this modular build to produce synthetic natural gas for a price of approximately €4.60 per kilogram synthetic natural gas. If we compare it to a kilogram natural gas nowadays, it is approximately 40 cents. So it's more than 10 times higher. However, we have to keep in mind that now we produce electricity with gas. at least a bit. But here we produce gas from electricity, so we have a completely different conversion cost. It is very comparable with other estimations for e-fuel synthesis. They are usually about 1 to 10 euro per kilogram. Yeah. Okay. So we studied the case a bit further. Sorry, and since we are able to store the gas, we checked the day-ahead market prices for electricity for the year 2020, and we thought like, okay, what if we only use the cheap electricity and we don't use the high prices? We have, of course, a few things that we have to keep in mind. We have to add storage into our system. Storage is expensive. And also we need more electricity because we have to generate more hydrogen. So we have a buffer. We call it, let's call that over-dimensioning here. And now, if we assume we have like 12 hours of electricity, 12 hours of storage for methane, and we have a dimensioning factor of 2, means we produce double the amount of hydrogen that we need. We can see this orange curve that is lower than the actual electricity curve. So we only use the lower prices, especially favored are negative prices, of course. And in this period of time here in September, we don't use the prices that are like 200 euro per megawatt hour.
Dr. Düner, do you have 2 more minutes, please? Sorry.
Okay. So if we compare that with the techno-economical data, we can see that the dimensioning, over-dimensioning will lead to a decrease of the electricity price as soon as we add storage. For example, let's take the 12-hour storage that I used before. With a dimensioning factor of 125%, we reach electricity prices of a little bit less than 40 euro per megawatt hour. And we can get as low as 37, 36 euro per megawatt hour. However, this does not compensate the higher investment for the PEM electrolyzer and the storages that we need. So in the year 2020, this is not feasible. Okay, so from the summary, we can produce synthetic natural gas. We can use synergy effects, and we can get a price of about 1.6 euro per kilogram synthetic natural gas. 40% of that price is electricity. The PEM electrolyzer is about 15%. And using storage and over-dimensioning is not economically viable in 2020. If we look at 2021 or 2022, where we have much more fluctuations, however, this could be a lot more feasible. And we can't wait for the end of this year to calculate the same thing with the higher fluctuations of the electricity pricings. First attempts show that we can save quite some costs by that. Okay, so this is the first step of our estimation, and we will continue further with more different setups to compare. And one of these setups will be methanol. Another will be syngas as well. So we're definitely looking closely at the syngas. Syngas, for example, is an important factor for this optimal system. So also saving of energy or heat recovery is a very important system thing because with high energy prices, this will have much more impact. And the next, the last connection to syngas, if we use a SOEC system where we could use a co-electrolysis of CO2 and water at the same time, we could directly produce syngas, and we are much more flexible with the process. We can much easier produce other fuels. We can sell that to potential buyers. So this will increase the flexibility of the process quite a lot.
Thank you very much, Mr. Düner. There is a question from Mr. Bleul.
Yeah, thank you for your presentation. No, I'm on. Do you hear me?
Yep.
Perfect. Yeah. Yeah, thank you. Great presentation. Question for your calculation, you're assuming a price on electricity which is stock market price. It's not loaded by any grid or whatever.
This is, I had not much time to explain. This includes the fees for the grid already. So we added the grid fees and so on. The actual electricity price for 2020 is about, I think, 30 euro per megawatt hour.
Okay. Thank you.
You're welcome.
And why not using electricity straight?
The problem is that not every glass will work with that. So, for example, amber glass, we have a lot of problems with the high amounts of emissions, and we also have problems including a lot of cullet. So there are attempts to solve these problems, but up to date, today these are not solved yet. And another thing is, of course, with a methane or methanol, with any e-fuel, we can store that. So if we have the problem that from any reason, like that the electricity is cut off, then we still have some backup system where we can run the glass furnace for some further time until we have anything to solve that problem. So it's a bit more resilient, I would say. However, it's more expensive.
Ferdinand, if I may just add something really quick, because the question arises a lot, why do you not build larger electric furnaces, or why do you not use electric furnaces for all the glass sectors? As you just mentioned, it's the usage rate of the cullet, but also it's the purification issues in flat glass industry, because if you have a vertical melting process, from what I have learned, you do not have such a big part of the melting tank for the purification of the glass. And especially if you go into high quality glass, like for example, flat glass sheets for windows, you need very, very pure glass with a very high quality without any bubbles or very high quality, and that's up to my knowledge, and also the electric flow and the whole process in the industry. You cannot just scale up an electric furnaces to a larger amount and scale up the quality and maybe scale up the glass you use, because it may seem not obvious, but from the chemical composition and the quality you need for the glass, a container, a glass bottle is very different from some special glass you produce. Thank you.
Thank you very much, Christiane. Mr. Bleul, can I invite you to, many thanks again, Ferdinand, for your nice presentation. We'll proceed with our last presentation for today. Thomas Bleul from Spanner Re will talk about your gasification technologies, and potential uses in industry sectors. Thomas, the floor is yours.
Yeah. Thank you. I try to get, let's see if it's working. You see my presentation now. Oops.
Yes.
Perfect. Thank you. Yeah, you catch me in first day vacation. So I'm calling you out of Sardinia, but yeah, it will be my only call during vacation. So yeah.
Thank you. Much appreciated.
Yeah, my name is Thomas Bleul. I'm CEO and founder of the company Spanner Re2, also part owner of the company. And we have been in the syngas business for the last 15 years now. Yeah, I was traveling the last years through Germany, and we have been discussing quite a few projects, how to use syngas and replacing natural gas. But with that price level we had over the last 10 years, we have not been able to make a first project. Things have changed, so we are now in process of having our first project, and company target for sure is having around about 50% of our sales in the next 3 years, and 3 years from now in replacing natural gas. So for us, it's a first approach now to glass. We have been able to approach different kinds of technology or different kind of industries already, but it's the first time to enter a little bit in the gas industry, in the glass industry. So we are curious and listening and learning. And what we always learn is that it's not easy to replace natural gas. So a little bit short, briefly through the Spanner Group. We are 4 companies. We are coming out of the automotive area. We are supplying to BMW, Porsche parts, and then we founded in 2004.
Thomas, your slide is not moving. Are you?
Okay, hold on. Here's something. Is it better now?
Put it in the presentation mode. Maybe you can put it on the presentation mode.
Now it's
you
gone.
Cannot see it now. Yeah.
Is it working now?
It's gone. No presentation.
No presentation. Okay. Hold on a second. I try it again.
If it does not work, I can also share it. I have the presentation. Yeah, it works.
Okay, now we are on the slide 3.
Now it's also moving now when I'm moving.
Maybe you can click this presentation mode, then it will move, I think. Yes, that one.
Is it working now?
Yeah, we don't see presentation mode, and now you're on slide 3.
Oh, I see presentation mode. That's fine. Well, if it's working like this, it's okay. Should I go ahead?
I'm not quite sure whether the presentation will be moving.
Is it moving now?
Nope.
No, shit.
Then maybe I can share it, or
yeah, maybe
no,
Olgo, you
nice. Yeah,
you try. And Thomas, you just tell Olgo when. Yeah.
Maybe we are good in syngas and not that good in presentation.
Maybe also your computer is on holiday mode. You never know.
Maybe I'm trying.
How do you see it?
Not the presentation so far.
You don't see my screen as well.
No, we see your Explorer.
Oh. How? Just a second, sorry. Oh. Now it should be working, does it?
Yes, it's fine now.
Okay, I have the PDF, but okay. Which presentation we are at? The second page, third page? Okay.
Okay, Thomas, now you're mute, or
No.
Thomas, do you want to continue? Cannot hear you. Thomas, we cannot hear you. Would you want to check in and out again to the call, maybe?
Or maybe join by phone?
Yeah, sorry, colleagues, we will give Thomas a little more time. Would be a pity, actually.
Okay, he's here. Hello.
Hello, I'm here.
Now we
yes,
hear you.
Excellent. Okay.
Okay.
So do you see the presentation? So if you would tell Olgo when to move slides. So.
Perfect. So we are coming out of the automotive area. We enter into renewable energies in 2006. We opened the company. Today we have on the Syngas side, on the biogas side, on the wood gas side, we have more than 900 plants operating. So we are very used on making out of wood gas electricity. We can go to the next page, please. That's the way one gasifier is working. You have in the middle the area where wood chips are passed through. On the right side, you have a reformer. And then the gas is cooled down, and then it's going to a filter system. And then you have already clean gas. What's our advantage? Why we are not moving towards big units is that we can produce a very clean gas right on the first step. So our gas is clean, tar-free when it's in the reformer or it's coming out of the reformer. Next page. The gasification process on its own. a little bit explained here on the side. I try to make a brief overview about everything, not knowing so exactly what the audience is, how much you have heard ahead of that on gasification. But basically, you have a zone where we blow in either air or we start blowing in water, steam mixed with oxygen. I explain later why. And we have an area where we have approximately 1,200 degrees. And at that area, if you manage that area well, you have tar-free gas. Afterwards, you have a reduction zone where you try to get as much carbon turned to CO to make your gas more rich. Next page. As of today, we are very skilled in operating on different kind of biomass. You see here a mixture of machines which are running more than 8,000 hours per year. And we also can contain bark, but we also like the wood chips out of the saw industry. It's important for investors to have more possibilities on purchasing the wood. Next page. We start operating machines on waste wood. Easy on that part is palletten, materials from pallet. We also are operating with, let's say, A2 wood, which is A2 material. A2 is everything what IKEA is. So if you shredder what you have at home from IKEA, it's A2 wood. We are running on Z2 a few machines, but here we are already facing a NOx problem. One step more, please. I also show here we have a machine in Augsburg, and that machine is specialized on trying out certain residues. And here you see a mixture between wood and this is a material PET. It's from the recycling area. So wood becomes only the structure of gasification, and we start trying out different materials. It's very promising, and we would like to increase because we always get asked where the whole wood should come from, where the whole biomass is coming from, and we would like to get independent on pure wood in the future. But we still believe a lot in the potential of wood-based biomass. One step further. This is a machine which is operated by Ecoloop close to Augsburg. It's also Sto has invested, and their target is to get rid of their styrofoam. Next page. We also are working on future fuels. And on the right side, you see pellets made out of waste wood and wastes from the plastic wastes. But these are future fuels where we are making tryouts. At the moment, we are completely focused on straight wood. Next page. So now we're coming to the Spanner Syngas. What are our properties? When we blow in air in our gasifier, the burner temperature is around about 1,400. So at the moment we are focusing in the industry on applications. We have our first order coming from brick plant. Brick plants have to achieve 900 degrees. Brick plants need gas 5 megawatt all year long. So pretty much same requirement like your industry is, that you have a 8,000 hours operation or a 24/7. Brick industry is moving the bricks every 20 minutes, 30 minutes, and then they need zero gas. So at that place where we have 1 megawatt on gas application now for tryouts, it's not funded. It's a regular. It's funded by BAFA, but it's not. It's like an industry. So they really would like, starting November, producing 20% of their gas from syngas. And the application is 900 degrees, and you have to be on, and then for around about 2 minutes you have to be completely off. And with our size of gasifiers, we can manage that we turn on and off. So what we're able to do is 0 and 100%. And if you have a lot of application next to each other, you can choose the gas volume you need. If 1,400 degrees is not enough, we made tryouts with CO2 and water steam, and then you have a pure gas without the nitrogen attached to it, and then the density of the gas is higher, and you also achieve higher temperature on the burner side. Yeah, as I explained, we can turn on and off, so we can be flexible to the industry. I think that is an advantage. What has to be watched is NOx. We are already having NOx out of the syngas production. We already loaded with NOx, and if you start burning our gas, NOx are added. So with the first tryouts we are making on using syngas in industry application, we are facing that our starting point on NOx is in burning side at 400. So same level as you have shown in your presentation. So when we burn our syngas at the moment, the first tryouts have shown 400 NOx. Next page. I give you a brief ideas how big setups can be. So this is for a dairy. We showed them 3 different setups. Milk dairy making gas and electricity. This is a plant around about 1 megawatt electricity and 2 megawatt of heat. Next page, please. These are the sizes. So the base side for 10 gasifiers is 30 meters by, can you go a little bit higher, please? Lower. And 13 by 13 meters. And this is making 2.5 megawatt on gas. And if you go higher level, as shown on the next page. Next page, please. If you go to a setup like this, you can make on 13 by 13 meters, you can manage 7.5 megawatt on gas. The last few pages are just some pictures to see what we're operating. Since electricity was not set high in Germany the last 10 years and gas was low, we have been all over the world. So we have been able to establish a few plants in Japan. We're already supplying to Thailand and Taiwan at the moment. And this is a 2 megawatt plant, 2 megawatt electricity, still with a lot of motors, a lot of gasifier next to each other. But the next step of development is going from a few gasifiers to one big filter system and reducing size and complexity. Next step. Why we have been able to make projects like this with a lot of CHP next to each other and gasifiers next to each other, there are not too many well-established gasifier processes outside there. The syngas history is with a lot of up and downs, and there are only a few companies which can show long references, and this gave us the opportunity to make these big projects. When we quote today, we quote more bigger motors, but we stay with the small gasifiers because it's very robust. This is also all the wood chips logistics which has to be involved. to get a good stream of biomass, you have to be able to also dry your wood chips and make it clean, get stones out, get metal out ahead it's hitting the machines. And we can go, I guess, to the last page. That was a brief overview. As I said, it's the first approach for us, and I'm curious about your questions. Thank you.
Many thanks, Thomas. Thanks also for working on your first day of holiday. So now the floor is open for questions. No, indeed. What from the organizer side, what I can say is that it was not so easy to put on stage a producer of syngas technology for this call or for this webinar today. So the floor is open for questions. Any questions? Yeah, it seems not to be the case. We've also exceeded our time, but Thomas, I have like you mentioned, like you come from the electricity and heat side. And now obviously currently the demand for syngas and natural gas replacements is very high. My technical understanding is not good enough to ask any specific questions on technology, but do you believe you can provide sufficient amounts and quantities and qualities for large industrial sectors, like starting from, like you have modular, you have rather small approaches which needs to be done modular. Again, like, what do you believe could be a time frame for you, as you now see this is an interesting market that will probably not go away? Are you bold enough to say you can produce the gas needed?
I mean, I'm really surprised by the volumes of gas we are getting approached now, or about industry. I guess I don't know what the plan was. But the volumes which are used in the industry and the inefficient heat use after the projects is surprising. So after your industrial process, you still have a lot of heat available for, let's say, heating or whatever. It doesn't have to be glass industry, but it's the industry we are facing. And for sure, as a company, we will focus on a few. We see, for example, thermal oil application is very attractive for us. It's 300 degrees. The brick plants are interesting for us. Glass could be maybe a little bit too big for us. I'm not, but if it's project with a, let's say, 7 megawatt gas usage, that's the size we think we are able to make. And and then you have to look on the material side. There was when I started going into the company, and we have been very excited about replacing with biomass fossil fuels, and at that time there was a guy here who was making a presentation. There was a picture set from Stuttgart, showing that worldwide energy consumption can biomass, the growing biomass is 10% of the, or no, 10 times as much biomass is growing as we consume as human beings. So on the premier factor side. And so biomass can be playing a certain role, but we're already facing that markets, biomass markets are also sensitive if big players are coming.
Thank you very much, Thomas. I would like to give the floor Christiane. I'm not quite sure, you mentioned you would need to leave. Christiane or Dr. Leicher, would you have any questions to Thomas? Basically, how could we get the glass industry with the syngas producers together? What could be next steps?
I think the first question would be, I may have missed that, but what kind of calorific values are we talking here? when your typical syngas, I mean, I guess you can add adjust it a little bit to your liking, but what kind of calorific values do we talk here in terms of megajoule per kilogram or megajoule per cubic meter or something like that?
It's it's low. Our regular gas is at 1.8 kilowatt hours per cubic meter, but
so
we
it's
mix
about 20% of natural gas.
Yeah, but we mix our gas 1-to-1 with air versus natural gas is mixing 10/1 or 1/10.
Yeah, okay.
So when we tried out a burner, a 200 kilowatt burner on natural gas is making 150 kilowatt on wood gas. That is what we learn when we have the same issue when we are selecting motors. We need to turbocharge or do something with the gas to use the bigger motors.
So
but
for what that means also
is,
what that means also is if you look at heat recovery, because this is something if you followed the chat, I know that Christiane and I had a little side discussion about low calorific fuels. And this is basically what we could do if you want to go for syngas of this quality, is to preheat the syngas like we used to do with town gas before we switched to natural gas and to heavy fuel oil. Because the challenge for the glass industry, in addition to NOx and things like that, which you addressed, is getting the temperatures. And if you have such a low calorific value gas, you will have relatively low flame temperatures as well. But what you could do is, and this is basically the problem that they had in the 1920s or so when they started using town gas or producer gas, which is basically just gasified coal. So it's similar to some degree. And what they did at the time was they used waste heat recovery to both preheat the air and preheat the fuel gas in order to get the temperatures that they needed at a decent efficiency. So that would be an option. Or you could have to think about some kind of oxy-fuel, but then of course you have a relatively cheap fuel, so to speak, a relatively low quality fuel compared to natural gas, and then you would have to use oxygen to get the temperatures up. So that's, but I think there are discussions. I know that there was a project in France a few years ago also looking into syngas from cellulose materials in glass manufacturing. So the question is probably not so much on a technical level, but again on the economical level and on the security of supply level.
Yeah. So our step to get a better gas, or not a better gas, to get a gas which can make higher temperatures would be water steam with oxygen. Then you have right away a very good. Yeah, you can make high temperatures.
Yeah, then you can also use hydrogen directly and oxygen. I mean, it's because water.
Yeah, hydrogen directly, then our reformer is gone. We tried that. We have been able to go up to 30%, and then it's became too difficult. Yeah, but
yeah, I mean, it's a challenge.
Water, steam, and hydrogen was working quite well. Water, steam, and oxygen was working quite well.
Yeah, I think it's a challenge, but it's doable. I think.
I mean,
I'm always saying nobody needs syngas if there's plenty of natural gas available. So
that's always the issue. I mean, it's something. Why go for something complicated if the easy solution is just on the other side? And I mean, that's the whole discussion. Why are we thinking about hydrogen or biogas or syngas or whatever? Because of this new constraint in terms of decarbonization. If you just want to have process heat, go for natural gas. That's the easiest way. Normal times. Let's put it this way. But this necessity for decarbonization changes the playing field a little bit.
I'm sorry, I have to rush to another appointment. I just wanted to add my question from the sludge gas. Klärschlamm came because I had a company contacting me. They made syngas from Klärschlamm from wastewater sludge, and they were drying
the wastewater sludge, and they used the heat somewhat from the drying to preheat the gas, and they said they could reach temperatures up to 1,600 degrees. So I thought that was kind of interesting. And maybe to look into it further. I just talked to them 2 days ago, so there was no time to include them into the webinar. But maybe I can talk to them further and explore how they if they preheat the gas or how they reach the higher temperatures.
Yes, many thanks, Christiane. So I believe like we are already a little late. So I would propose the following. We will many thanks to all speakers and contributors. I think was an extremely interesting webinar, like shedding light from different sides. Obviously, the final statement was, okay, natural gas is a good fuel. You know, why leave the fuel? But we know the answer. I'm not going to repeat. I propose that, also supported by the RE4Industry project, we will think of having follow-up webinars where maybe we can focus on specific sub-questions or invite other syngas producers. And we will keep you informed. Many thanks. I think that was basically the first webinar on the issue, co-organized by RE4Industry. And I would propose that we close it now. You will receive the information how the recording and the presentation can be viewed later on by my colleague Olgu. And with that, we close, and together also with Christiane and Hendrik and the project partners, we will move forward on this issue. You will hear from us in the coming weeks. And yeah, finally, Thomas, wish you a nice holiday in Sardinia, no?
Thank you. It's okay. Ciao. Thank you.
Bye-bye. Have a nice day.
Hey, everyone.
Have a nice day.
Thank you.
Bye.
Thank you very much. Bye-bye.